In this video, we're going to take a look at isoelectronic series that relates to ions, and then do some drawings of ions as Bohr-Rutherford diagrams and also as Lewis dot diagrams, and we'll apply that to standard atomic notations and also standard ionic notations. So what is an isoelectronic series? Iso essentially means the same or similar. So same electron series. So a series of ions that basically have the same arrangement of electrons. And so remember that when ions are formed, they become kind of like noble gases in a way. If you remember over here, when we form an ion, let's say we're forming an ion with sodium here, sodium is losing an electron. Below, we have a full valence shell. So it became almost like a noble gas because it's stable and has a full valence shell. And chlorine, well, it gained an electron and it became almost like a noble gas because it has a full valence shell. So isoelectronic is basically a collection of elements that have similar electron structures, and we can compare them to noble gases. So if we look over here, sodium is isoelectronic to neon. Magnesium is isoelectronic to neon. Oxygen and fluorine ions, these ions I should say, so I should say sodium ion, magnesium ion, are isoelectronic to neon. The oxygen and fluorine ion are isoelectronic to neon. So by gaining electrons, oxygen became like neon. Oxygen had 8 electrons at first and gained 2 electrons to become an ion, so it became like neon. Fluorine had 9 electrons at first and gained 1 more to become an ion, and it became like neon with a total of 10 electrons. Sodium had 11 electrons, but it lost 1, right, on its 1 valence shell. And so now when it becomes an ion, there's 10 electrons like neon. Magnesium had 12 electrons, but to become stable, it lost 2. And when it loses 2, it has 10 electrons like neon. So this series of substances, ions, and elements are isoelectronic to each other. The negative ions, the anions, are isoelectronic to the neon, and the cations are isoelectronic to the neon as well. There's actually a little pattern, a little trick you can use to figure out what an ion will become isoelectronic to. So if we go to our periodic table, notice that, for example, fluorine wants to gain a valence electron because it already has 7 and wants to gain 1 to become 8. When it gains 1, it becomes like neon. Oxygen wants to gain 2, but it becomes like neon, right? It'll have 10 electrons in the end. Nitrogen will gain 3. It becomes like neon. So nonmetals, they will become like the noble gas that comes right after them. So nitrogen becomes like neon. Oxygen becomes like neon. Fluorine becomes like neon when it forms an ion, when they form an ion. So we say that the nonmetals are isoelectronic, nonmetal ions are isoelectronic to the proceeding noble gas. So let's go fill that out, proceeding noble gas. So to the proceeding, that means the noble gas that comes after them. Noble gas. So fluorine, its ion, the fluorine ion, is isoelectronic too. So let's go take a look at the noble gas that comes right after it. So whoops, let's go over here. So here's fluorine. It's going to be isoelectronic to neon when it forms an ion. So let's go ahead and write that out. It's going to become isoelectronic to neon because fluorine has 9 electrons, but when it becomes fluorine minus 1, it will have 10 electrons, which is basically what neon has. Neon has 10 electrons. So now they're isoelectronic to each other. Nonmetals become like the noble gases that come after them because they're gaining electrons. Now, metals are a little bit different. Metals, for example, beryllium will lose 2 electrons. It won't become like neon because it didn't gain 6 electrons. It lost 2. It had 4 and it lost 2 electrons. So what has 2 electrons here? Well, oh look, helium. Lithium has 3 electrons. It has 1 in its valence shell. It loses 1 to have a stable shell below. So when it loses 1 electron, it has 2 electrons left over. What has 2 electrons? Oh look, helium. So the nonmetals kind of move forward, move towards the right side. But the metals, they lose electrons, so they go backwards, sort of. So, for example, magnesium had 2 valence electrons, so it loses 1 and then 2, goes back to neon. So if it had 12 electrons to begin with and loses 2, it now has 10 electrons. So metals, when they form ions, they become isoelectronic to the preceding noble gas, the noble gas that came before it in terms of atomic number, preceding noble gas. So let's go ahead and write that out. To the preceding noble gas. So for example, the lithium ion is going to be isoelectronic to helium. So those are called isoelectronic series. So let's go ahead and do a couple of examples for drawing ions for both for Bohr-Rutherford diagrams, Lewis dot diagrams, and standard atomic notations. And it will also figure out what's isoelectronic to what here. So let's go ahead and draw a Bohr-Rutherford diagram for regular magnesium. There's no ion there, so just magnesium. So we go into our periodic table and look for the square for magnesium. So I'm just going to kind of draw that out over here. Magnesium is 24.31, which I'll round down to 24. Mg is a symbol, and then 12 atomic number. So we'll draw our nucleus with 12 protons, and also 24 minus 12, 12 neutrons. Since we're drawing the neutral element, we're going to have 12 electrons, so 2 on the first shell, and 8 on the second. And then lastly, on the valence shell, 2. Now, magnesium is a metal. It has 2 valence electrons. Is it easier to lose those 2 to have the full below, or easier to gain 6? Well, it's easier to lose 2. So we're going to redraw the magnesium as an ion, having lost the electrons on the outer shell. And so it's only going to have the electrons below it left over. So we're going to redraw everything kind of the same way. We have still 12 protons. Protons don't change. 12 neutrons. Neutrons don't change for this particular atom here. We're going to draw our first shell with 2. Our second shell is still full. And we're not going to draw our last shell because we got rid of the valence electrons. But what we do is we put a little bracket around it, square brackets like this, and we put plus 2 on the outside because you lost 2 electrons, it became positive 2. Since this is a positive ion that was formed by loss of electrons, this is a cation. Cation means positive ion. And magnesium, what noble gas would it become like? Would it become like argon? So will it go this way, so gain 6, or will lose 2, so go back here and then all the way back here? So it looks like it's easier to lose 2. It goes backwards. So it loses 2 and it becomes isoelectronic to neon. So magnesium is isoelectronic to neon. And the charge makes sense, right? It's in group 2. 2 valence electrons lose 2 electrons. So that's how a cation forms, by loss of electrons. And try to think about where those electrons went, right? Where could they have gone? So remember, electrons, they're not going to go in, they're not just going to disappear and float around in thin air. They're going to go somewhere else. So think about what would want those electrons. Right, probably a nonmetal, because nonmetals gain. So maybe those electrons are going to a fluorine or to oxygen in some way. So let's draw out a Bohr-Rutherford diagram for fluorine. So fluorine, I'm just going to round everything here, has a mass of about 19, and then atomic number of 9. So we're going to draw our nucleus, 9 protons, 10 neutrons, and if it's neutral, there should be the same number of electrons, so 9 electrons. So 2 in the first shell, and then 7 left to place. So 1, 2, 3, 4, 5, 6, 7. So now we need to think, is it easier to lose these 7 or gain 1? It seems like it's easier to gain 1 and become like neon. So we'll gain 1. We'll redraw this out. Same number of protons, doesn't change. Same number of neutrons, that doesn't change. But what's changing is the number of electrons. We're adding one more. We're going to add one more over here. Maybe it came from magnesium. Maybe one of the electrons that the magnesium lost is going to the fluorine. So we're going to go like this over here. Draw the ones that we had before in place. And just to show the difference that this is the one that's being added, I'm going to put this here as an X. And then I finally just put my square brackets, and I put a charge. And the charge, since it gained only 1 electron, is -1. You could have put -2 if it gained 2 electrons, for example, like oxygen. Since it's is negative, it was formed by a gain of electrons. This is an anion. Very straightforward. So we just saw how to draw the neutral Bohr-Rutherford diagrams, which we reviewed earlier, and now we drew the ions for the Bohr-Rutherford diagrams. Now let's take a quick look on how to do that for the Lewis dot diagrams. So neutral Lewis dot diagram, just draw the symbol and number of valence electrons, 2 for magnesium. Magnesium is a metal, it loses 2 valence electrons, so you simply draw the symbol, no more electrons around it. You're not going to draw in the remaining electron, you're just going to leave the symbol as is, just like a naked symbol, and then you're going to put the square brackets around it and put +2, because it lost 2. If it was a metal that lost 3 electrons, you would have put +3. But either way, metals, when you draw the ions, you draw them without electrons surrounding them because they lost the valence electrons, and then you just put their charge around the square bracket. For non-metals, so let's go ahead and draw the Lewis dot diagram for fluorine, just a neutral fluorine, like that. For fluorine as the ion, it gained an electron, so we're redrawing the neutral, and then we're just adding the extra electron there. If you added 2 electrons, you would have added 2 electrons. If you added 3, you would have added 3. But what's different is going to be the charge that you indicate. So you put square brackets, and then you put -1 here. If you added 2, it would have been -2. 3, it would have been -3. Okay. So that's how you would draw ions for your Lewis dot diagrams. We'll do one more. Let's quickly do oxygen. So oxygen as a Lewis dot diagram has 6 valence electrons. If you want to draw its ion, it's easier to gain 2 than to lose 6. So like this, and I'll put the 2 additions here. They could have come from the magnesium. It could have formed magnesium oxide. We'll put our square brackets, and we'll put -2, like that. So standard atomic notation, we've seen that before. We draw the symbol first, put the mass up here, put the atomic number over here. Really nothing is changing when you're doing it for the ion other than you're putting the charge. You're still going to have the same mass because the electrons don't really add or take away from mass really because they're so light. You're still going to have the same atomic number because it's still the same number of protons. But what you're going to have here is the +2. Same idea. Fluorine has mass of 19, atomic number 9. For the ion, it's going to be the same idea. But you have to put the charge of -1 here. So essentially what this tells you is you have 12 protons here, 12 electrons, 12 neutrons. Over here you have 12 protons still. But since you're +2, it means you lost some electrons. You lost 2 electrons, so now you have 10 electrons left. But your neutrons are the same, and so are your protons. Over here, this tells you have 9 protons, 9 electrons because you're neutral, and then 10 neutrons. So neutrons don't really matter too much when we talk about ions. But for our ion, we still have 9 protons, based on the atomic number. But since we're -1, we gained an electron from what we had before. We have 1 more electron than we have protons, so 10 electrons, and then 10 neutrons. So notice protons and neutrons stayed the same, but electron number changed when it came to the ions. So the last part here is just a little reminder of the trick to find the charge for the ions in the periodic table. And now you're able to draw ions in various ways, and you're able to explain isoelectronic series for ions that form, whether they're metals or they're nonmetals.